Have you ever wondered how a metal can be both incredibly strong and surprisingly lightweight? Today on Tutor For Me, we're exploring titanium, a remarkable metal used in airplane engines, medical implants, luxury watches, and even space technology. But titanium doesn't start out shiny or refined. Its journey begins deep within the earth. So how is titanium made, and why is it considered one of the most valuable engineering materials in the modern world? Let's find out. Titanium does not occur naturally as a pure metal. Instead, it is found in rocks known as ores. The two most important titanium-bearing minerals are ilmenite and rutile. These ores are usually extracted through open-pit mining. Countries such as Australia, South Africa, and Canada are among the world's leading producers. Once mined, the ore is crushed and washed, separating titanium-rich minerals from unwanted materials. Interestingly, titanium is the ninth most abundant element in Earth's crust, yet it is rarely found in pure form. This is because titanium bonds very strongly with oxygen and other elements, making extraction a complex scientific challenge. The most common method used to extract titanium metal is the Kroll process. This process was developed in the 1940s and is still widely used today. First, the ore is mixed with chlorine gas and a carbon source, such as coke. This mixture is heated to temperatures of around 1,000 degrees Celsius. At this extreme heat, titanium reacts with chlorine, forming titanium tetrachloride, a volatile liquid. At the same time, impurities such as iron are left behind as solid waste. The titanium tetrachloride is then purified through distillation, removing any remaining contaminants. Next comes the reduction stage. The purified titanium tetrachloride is reacted with magnesium, or sometimes sodium, inside a vacuum or inert environment. This reaction produces titanium sponge, a porous, brittle form of the metal, along with byproducts such as magnesium chloride. Although it doesn't look impressive, titanium sponge is a foundation of all titanium products. To turn this sponge into solid metal, it must be melted and refined. This is done using advanced methods such as vacuum arc remelting or electron beam melting. During this stage, the titanium sponge is melted in a vacuum, removing remaining impurities and ensuring uniform quality. The molten metal is then poured into molds, forming large blocks called ingots. These ingots are reheated and shaped through forging, rolling, or extrusion, producing sheets, rods, tubes, and other industrial forms. One of titanium's greatest advantages is its ability to form powerful alloys. By adding small amount of elements, such as aluminum or vanadium, engineers dramatically improve titanium's strength, heat resistance, and durability. These alloys are especially important in aerospace and automotive engineering, where lightweight strength is critical. This ability to customize its properties makes titanium one of the most versatile metals ever developed. After shaping, titanium parts undergo machining and finishing. Titanium is difficult to machine because it is hard and retains heat. Specialized tools are required to cut, drill, and shape it precisely. Medical implants are often polished to a mirror-like finish and treated to improve biocompatibility. Aerospace components, on the other hand, receive heat treatments to enhance strength and fatigue resistance. Despite its incredible benefits, titanium production does have environmental costs. Mining and processing require large amounts of energy, and the Kroll process produces chemical waste. However, titanium has a long lifespan and is highly recyclable. Many titanium components can be reused, reducing the need for new raw materials. Researchers are also developing more sustainable production methods. One promising technique is the FFC Cambridge process, which uses electrolysis to extract titanium more efficiently. So why go through all this effort to produce titanium? Because titanium offers a rare combination of properties: high strength, low weight, resistance to corrosion, and the ability to withstand extreme temperatures. These qualities make it essential for aircraft, rockets, medical implants, sports equipment, and luxury goods. Titanium even has a unique appearance, With a silvery gray color and the ability to develop vibrant surface finishes, titanium's journey from raw or to finished product is a powerful example of human innovation. It shows how science, engineering, and persistence can transform ordinary rock into extraordinary technology. As materials science continues to advance, titanium's role in shaping our future will only grow. This has been Tutor for Me. If you found this video helpful, don't forget to like, subscribe, and share. And let us know in the comments, what material should we explore next?